Today I would like to talk about DSFM. This was the abbreviation, Dynamic Semi-Parametric Factor Models. And originally I wanted to just show the application to implied volatility, but recently the co-author Szymon Borak, who is here in the audience, and he will show a talk based on this technique applied to so-called skew hedging this afternoon or tomorrow. And this is also joint work with Enno Mammen from Mannheim and Björn Park, and Rafael Veron contributed from Wrocław, Breslau, contributed the electricity pricing example. I start with a very simple educational statistical task, because next week we have a so-called Dean's Dinner, and the finance minister of Berlin will be there, and I have to explain what is important in statistics. So one important thing in statistics is, as you all know, fitting a model. So I show you here 1, 2, 3, 4, 5, 6, 7 data points, and one simple model could be a linear regression line. Now I make it more complicated for this finance minister. I show him 2 lines. Yeah? And so 2 lines, and now these 2 lines could be one data set at one point, and then the other data set observed at some second point. Now you could ask the typical question, the statisticians all know this kind of question: is the slope the same, or are the x's the same, or are the intercept the same? I will show you a little bit more complicated situation. I will go into higher dimensional space. I will show you simultaneous regression here. Suppose this is time point 1, this is time point 2, this is time point 3. So you get to see at time point 1, you get to see this data. At time point 1, you see on another tranche of data, but simultaneously you see this data set. And so here you observe the following. Data set 1, data set 2 was the first 2 regression lines, and then you see it seems to stay linearly all the time in this component of a multi-regression setup, but as you can see, the pattern, heteroscedasticity pattern changed. And this all looks as you could fit some kind of sine basis function, or maybe here a parabola, but sine basis function, again with some non-homogeneous pattern of design and of error. Here you see clusters, and here you see x variables that cluster even more. Now you could say this is really made up. In fact, it was made up educationally, but I'll show you a little film of the electricity forward prices. I told you this is the data provided by Rafael Veron. If I make an error in the description, Szymon Borak will help me here. Essentially here you see the number of days, so essentially 2 years, and you see the price of electricity, and it's measured in NOK divided by Norwegian crowns. It's for some historical reason, because Norway has lots of water falling down or flowing down, so that you can create electricity easily per megawatt hour. And this is the price of the electricity that you would buy on this exchange market from this time point down to the next one. Now, why is this related to this changing regression in time? So if you let time flow, so here for example you see the March 1999 situation, you see this data moves like a film over time, and it is very interesting to understand. You see some yearly pattern here, some seasonality, but you see that when we want to model that, we just don't look at one particular time point. We have information over time that we would like to use. Okay. Another standard example is this one, but I have a film. It should be here. Here. This is my other standard example that you might know. Many of you have probably seen this before. It was mentioned before, the implied volatility. Yeah? Everybody in this room knows the Black-Scholes formula, a one-to-one map of the Black-Scholes formula to the so-called implied volatility as a function of moneyness. This is moneyness, so here you have the ATM point, and here you have maturity, and you see red points going up and down. And these red points are actually the implied volatilities of the German DAX on the German DAX index. Here in this case it was September 2001. You see what will happen. We're moving into 9/11 here. You see a lot of variation, and the question is, how do we model such rather rich structure over time? Okay, I will show you another film. So this is a later data set. All these data sets, remember, all these data sets, they are very interesting and very unique. Only we have them, and you can get them for free. If you have a reasonable project, right, that you write to Lucille Brandt and I, we are the director and deputy director of the SFB. You can come here and work on this data set. You see, the structure is that we have time points. At each time, here's the time. At each day, we have several points that move through space. Okay, so let's move back to the talk. Okay, so that was the finance example. Finally, a medical example. This is a typical, the typical way of showing slices through a human brain. In this case, we took 15 different horizontal slices, and it also moves over time. And I'm just showing the way how it moves over time. The red points here are intensity over median or over mean, over the mean. So, yeah, you have to understand this human being. This is just one slice. This human being that sees that has this intensity. It looks at rotating green telephones, at rotating blue bikes, etc. And so one wants to find out certain patterns here. This is actually a very old kind of research in the Air Force. One has done this with electroencephalographic signals. End of the 70s, my first job actually started with this kind of data analysis on EEGs. Now it's fMRIs. But let me do it, let me put this into a more formal mathematical framework. All you have seen now in these films and in the financial, in the electricity example, and also in the medicine example was the following. You had data at time point t equal 1, and you had J1 data points. You saw that this moved over time, yeah, at time point T1, we had J1 data points, at time point T2, we had J2 data points, etc. Yeah? And what we are interested in is in describing, if you remember this blue surface, this was a so-called Nadarai-Watson estimator. We assume some noise here, and we try to describe dynamically this very high-dimensional surface, right? So like you have seen how the implied volatility surface varies over time. So we have to combine a smoothing problem and a structural, say, parametric or a structure over time. Now, of course, you could make your life easy and say, well, I put everything into a big pool, and then I just have a global regression curve or global curve F. But that's certainly not interesting. What you would like to do is to find some structure over time. Now, this is, again, a very old problem, but we will put it into a new, we shed some new light on it because we put it into the so-called semi-parametric factor model. I'll explain in detail how it is related to functional principal components, to varying coefficient regression, to panel data analysis. The model that we will use for modeling these three data sets that you have seen is based on capital L factors. That's why it is called factor model, okay? And these M's we don't assume to be known, but the M's are depending on external variables, right? For example, this moving over time maturities and moneyness points in the IV film, and the Z's, these Z's, they are constitute a multivariate time series of which we then assume, or econometricians would, for example, apply a vector autoregressive model to them to understand the dynamic of Z over time. Okay? So once again, we have a low-dimensional factor model. Capital L is the number of factors, and M in this case, vector of basis functions, we could say, or factor functions, they represent the time invariant structure. The trick in this research is that we also estimate the basis functions from the data, and then also estimate actually the z's, right? So we have z's, and now I give this, for example, to my colleague Helmut Lütgepohl in Florence, or his two students Brüggemann and Tränkler, that have now that are were in this collaborative research centers and have now chairs in Mannheim and Konstanz. And then I ask them, can you tell me the VA dynamic of that? What will they answer? What will they ask me? What will be the first question back to me? They will ask me, am I allowed to do that? Because you are estimating the factor function. You are estimating these sets, right? So the question is, if this econometrician does his inference, his VAR estimation based on the estimated ZTs, right, is he doing the right thing? As if I could give him the theoretical ZTs. Yeah? So that is one of the theoretical questions that we address here. I don't have to tell you that it is interesting to know this low-dimensional dynamics. Yeah? So what we see is we see a high-dimensional surface varying over time. What we are doing is we decompose it into simple understanding functions that we run with a low-dimensional dynamic. So it's a kind of dimensionality reduction over time. That was my advertisement question to Ronnie before, when I asked him, did you do this, say, IV correlation or this ITRAX or CDX? He'd shown 3 of these curves. Did you show it over time? Yeah? All right. So I'm interested in studying this over time. So that was the motivation. Now let us look at the model one more time. So let me take this first function, M0, sort of the constant basis function, which has loading 1. Let me also take it into the model. So this index starts now with L equal to 0. So I have a very simple linear structure. The question is, how do I model M? Okay. Modeling M, or simplifying the model in different directions, has been, as I said, a very natural and old task. So here is, for example, the so-called orthogonal factor model. But in this case, there are no external variables. So the M's are just vectors MLJ. They don't depend on X. So then you boil down, here's a reference, Pena and Box. You boil down to an orthogonal factor model. Or you could say, oh, the errors. It was legal here since Volodya's talk to say microstructure noise I put into the error, or bias I put into the error, right? So I put some structure into the error and call it now a panel model. Yeah. So, but it's a different error. So I just this is the time panel structure. This is the individual effect. You could also see it like a panel model with different error structure. You could also say, I've seen this model before. Suppose I see Z's and I see X's, then this is nothing else. If this were not there, it's just linear regression, right? And this would be the coefficient. And if I assume these coefficients depend on external variables, then this thing is called varying coefficient. But we observe the Z's, okay? I don't observe Z's in this general DSFM model. So here's a reference, Cleveland, for example. Or you could say, I have seen this before, I call it time-varying regression. But what is the difference in time-varying regression? Then you take capital L exactly equal to D, and the ML functions are a function only of the Lth coordinate. Or you could call it a parametric factor model in interest rate models, for example. You just assume a certain form, some exponential or logarithmic form, and it will boil down to a well-known model used in finance, Nelson and Siegel, okay? Or functional principal components I mentioned before. So what is the difference to all these models that look very similar but have different components and assumptions. One is the orthogonal factor model is different because the ML are functional loadings. Varying coefficient assumes Z to be known, but we observe the Z's not to be observable. And you find a lot of differences that motivates us to study this so-called dynamic semi-parametric factor modeling approach. In a paper that comes out now, has just appeared in Journal of Financial Econometrics, we have used this. This is the joint authors here are Enno Mammen, and this is Matthias Fengler from now with Saal Oppenheim. We use this kernel estimator approach, but we in our science it is possible to publish papers and write papers without proving that the Zs and the MLs converge and solve these econometrics questions. We found out it's too difficult for this kernel estimator, so we used this explicit B-spline approach, which is.
So far, you have put no assumptions on Z, just any free parameters, or
you will later, of course, we will have a parametric time series structure on the Z's.
So
yeah.
far,
Yeah.
just completely so many parameters.
I'm just showing the possibility of this model. Now, which model would you like for Z? I mentioned already an econometric model, a VAR model, for example. We can put this in, and then we will show that the maybe you wait for the theorem, but we will show you that there's no cost in knowing the Z's or not knowing the Z's. And in respect to the parameter estimation of the Z process. I'm concentrating on the Z process.
Z is like Newton's parameter, and you are at the moment focusing on M. And if you estimate the M loadings, then you actually don't need a model on Z.
No.
You can use just for every T difference. Is it correct?
I don't think so, no. It's more or less like a semi-parametric situation. I'm looking at the parametric structure of the Z, of the Z's. And I'm saying there's no cost in not knowing the M's, right? But I have to estimate the M's, that's why that's why the Z's are also estimated. And you will see that there is no cost or a low cost in estimating the Z's. Huh? Okay? Okay, so we have used this model sort of more or less empirically. We have we have used this fitting technique more or less empirically to estimate C's and M's, but we had no theory for it. Right? Now, but the theory will come. Now we show you theory for an explicit B-spline estimator. So this is the I use a B-spline expansion for the M. Okay? With known basis functions. I will show a picture later of the basis functions. And that means you rewrite the model in terms of Z's. Here are your, coefficients for the basis functions. And the task that, the estimation procedure that we are doing is to fit, in a least square sense, to fit the A and the Z's to the Y's. Yeah? Wait a second, this is of course not so easy. The minimization problem has no unique solution. You can rotate, of course, the A's here and the Z's. If you take a minimizer ZT hat and A hat, you can take an arbitrary matrix of this form with an invertible matrix and you will get also a minimizer, but it will not affect ourselves because we are interested in estimating the space of the Z transpose A. There's a convergence result. I would like to say we have no answer here on the following three smoothing parameters. We have no idea yet how to fit the dimension of the time series. So AIC has not been, or similar model approaches have not been developed. We also have no rule on how to select the number of basis functions. We have sort of asymptotic results that says let's say k has to be that and that speed relative to L or relative to the dimension of x. And we also have not studied the type of basis functions. We will use B-splines in a picture you will see in a few transparencies later. Okay. Now, what did I say? We want to show that when I do a var model based on ZT, or any parametric model based on covariances, I should say, that there's no cost in using the estimated ZT.
Exactly means you have some kind of structure on loadings on M, you have no structure on Z at all. Z is as it is. And this means Z is, when you're estimating M, your Z is like a nuisance parameter and you have kind of adaptivity. This means you actually
You can forget the Z's. Or, but I can also say I forget the M's. Because for estimating theta, the parametric model for Z, you will see it. Welcome.
It's a moment.
I'm just, yeah, in a moment.
Now, it's like you first step you estimate M and Z is a nuisance parameter. The first step. This first step, Z is really unimportant. You can work with the full complexity.
Good. I'm working on something unimportant which will have some importance later.
Yeah, but then you turn around.
Yeah. Okay. Yeah, you can put it this way if you want. But I'm concentrating on as I said, on the asymptotic negligibility of estimated covariances based on the estimated Z and the estimated covariance based on the observable Z. Yeah. So any model, like for example, var model with parametric structure based on covariances will allow me to use the estimated Z's instead of the Z's. Yeah, you will see. Please wait 1 second. So I'm close to formulating the main result. So let us take one of those minimizers and let us take this matrix B here. And you can see with this matrix B, we are spanning the same space. Yeah. Let us take this matrix B and now let's look at these rotated Z's. Then we can show the following. Suppose God gives you the true Z's. Yeah? He gives you the true Z's. Then you look at the covariance of the true Z's. You estimate the covariance of the true Z's, covariance matrix. And here are the estimated Z's. And you see this difference is of smaller order than t to the minus 1/2. So over time, you learn from the estimated Z's. Okay? Let me make this evident with this standard econometric example that I explained, a var P process. Okay? So, of course, this var P process fulfills our assumptions. This is a var P process of order P, as you can see here. And it has these parameters. Yeah? Here matrices A1 to AP. So this is the theta vector. Yeah? We know very well that from econometric theory or from very old results of Joule and Walker, we know that this is asymptotically normal, and so the right scaling is square root of t. That's why I had to show, and of course the thetas are estimated from the covariances of the z's or the estimated z's. Okay, so what this result says in one line, it says take the estimated z's. Yeah? Compare it with the true value, blow it up with square root of t. Then you can decompose it. You see, you can just plug in this theta hat. You can decompose it into something that is of smaller order. So this is the theorem that says this is of smaller order. Yeah? And the term that becomes asymptotically normal. Is this what you expected?
I don't know. Probably this is in your case, it's a good feature. It's kind of adaptability, you can decompose.
Yes. Okay, good. Let me show you. I have a graphical, as you know, I like graphics. I have a graphical representation of this, say, theorem. Yeah. So let us simulate Z's from a VAR model. And I show you the simulation here. This is the VAR model. So 3-dimensional, so capital L is equal to 3. You have a VAR model. Here's the coefficient matrix. Here is the corresponding covariance matrix of the errors of this VAR model. Okay? And we use those basis functions. So capital L is equal to 3, as I told you. Okay, how do they look like? They look like this. This is one, this is the second one, this is the third one. Okay, and we use the following simulation setup. We use, it's 2-dimensional, as you have seen, 3 settings. One with 36 knots, one with 49, and one with 64 B-spline knots. We use 500, 1,000, and 2,000 days. That means the time series runs 500, 1,000, or 2,000 days. And capital J, sort of the number of data points at each day, is 100, 250, or 1,000. And we repeat this every 200. We repeat it all together 200 times. This is the definition of B-splines. It's much nicer to show it graphically. So these are the kind of basis functions. Here you have it for 36. You see 36 basis functions. So all those get multiplied with one of the elements of this capital A matrix to form and to approximate this.
What order are these B-splines? Cubic or B-spline is a general term for that. What order is this spline?
This is, if I see this, you say,
It's linear.
yeah, linear. And you could see it. I mean, there are little pyramids. It's little pyramids.
Yeah, it was not sure whether it's
Really? Bad graphic.
no, it's my bad eyes.
Good. I thought it was clear, but okay. So tensor B. But this is the theorem. Can you see why? When I ask this question, my students, the answer is always on the transparency. Okay, but I will read you the caption of the transparency. Okay, so what you see here is, remember it was the following example. We are still in a simulation. Yeah, remember the simulation part. We have generated now a DSFM model with this, so we know the model, so we can see what will happen with these Z series, right? And we did it 250 times, as I said. Okay. And now I'm showing you the differences here of the elements of the covariance matrix here based on the estimated Z, okay? Based on the estimated Z. So this is for situation number 1 where we have 500, this is for 1,000, this is for 2,000 data points, okay? So we have a 3-dimensional example, so we have 3 elements of 3 differences of the covariance matrix, so to compare. So these are the box plots over the 250 simulations, and this black line here is the quantile for the true Z. Suppose, I mean, God gives me the true Z's. I'm estimating this VAR model. I'm estimating it 250 times, so I can calculate the 5% and 90% quantile. So what do we see here? We see that the variation, as I said, is well within these quantile bands. So the theorem, this kind of plot shows very nicely this little OP structure. I claim now that in this graphic, I'm actually a little bit too pessimistic. I'm showing you something that that I could show even more positively. And why? Because I'm showing you with the bold lines, I'm showing you only the 5% and 95% quantile. Okay? But you see here the so-called whiskers. These are the whiskers of the box plot. Yeah? The whiskers of the box plot. So these whiskers are completely inside the 5% and 95% quantile. Does anybody know where the whisker for a box plot lies when the data is normal? This is real data analysis. We teach this our students in multivariate analysis 1 in the 5th semester. I tell you, okay? So because you don't know, you don't remember the whisker, right? That's the thing. The whisker is defined as the interquartile range. Excuse me?
And you reward for beard.
What? Okay. So the interquartile range of a normal, yeah, you have to calculate that. And then the whisker is defined as 1.5, the interquartile range. Yes? So it's the whisker for a normal data set would not be, the whisker height here, right, would not be at 95 or 5%, it would be rather at about 99.5%. Right? So I could have shown you, I should have probably shown you to make this even more positively, the more extended versions of the black lines. But this way I can always ask you this little nasty question. Okay, so you have seen these differences of the scaled covariance matrices here. So this is from the estimated data, this is from the true data, and these are the true differences, yes? So these are the true differences, so the true variation around its asymptotic covariance. Okay, so let us now apply this to implied volatility analysis, and you will see an application later tonight. Shimon, is this tomorrow your talk or today?
Tomorrow.
Huh?
I hope today.
You hope today. Okay, good. Well, we have a change program, so anyway, you will see two applications of this DSFM models to implied volatility and to pricing kernels that vary over time. Okay, I think this is transparency that I don't have to show here. It just tells you how implied volatility is calculated. I've shown you this film already, the degenerated design. The data that we are looking at here is from 2004 to 2005. And I made already this marketing advertisement here for the FEDC, Financial Economic Data Center. And we did, as I told you, we don't know yet how to select L in this modeling approach, but we did some kind of preliminary elbow criterion approach here by looking at this residual variance or this relative variance resolution as a function of L. You see that you have at about 2 or 3, you have not really a significant or a really good variance improvement in this fit criterion. So that
I think it may have been on one of the slides you skipped, but how do you worry about keeping this arbitrage free in this application? In other words, you have to constrain it. You can't just fit any surface to that thing, and you can't allow it to.
We have not done it yet. It means that you would. I know what you mean. You cannot just use this blue handkerchief approach, right? Or this, because smoothing will create some arbitrage, right? Okay. Certainly. This must be done by constraining the coefficient. We have not done it yet. So we are equal, right? You have done it, you don't have done something I have not done.
Yeah, but statically it's very hard. Because statically it's really relatively okay to make sure the surface is free. But then dynamically it's not free to move.
That's interesting, yeah.
Anymore.
Definitely not, yeah. The x? Okay. The x is here. These are the x's. Remember? Moneyness and maturity, but it moves.
But you say you have 5.
Excuse me?
What are the other 3?
You are mixing x's and m's now, or what do you mean?
The X.
Where's x here? This x is two-dimensional.
Okay. Fine.
I must have, okay. The m function operates on that. You will see the m function, how they look like. This is one of them. This is the first one. This is the second one. Maybe they are too non-parametric, too flexible, but as I said, we have not yet, we have no idea yet how to select k, the number of basis functions for the B-spline basis. Okay, here you see the time series of weights ZT1 or ZZ2. Yeah, so this is over this time period from July 2004 to July 05. And if you look more closely at if you take the submodel, that means you just take capital L equal to 1. You look at the VDAX, you see that you are reproducing the VDAX nicely. There's a little zoom for the November period. And in modeling now the Z's, we fitted with the Schwarz-Hennen criteria var1 and with the AIC var2. This is a well-known fact that with Schwarz-Hennen or BIC-like criteria, we will have a lower dimensional model than with AIC. Econometricians here, I'm not an expert in econometrics. Econometricians tell me here this is a good situation. So this part that I'm reporting here is part of an analysis that I did with Julius Mungo, who is here, Ralf Brüggemann and Carsten Tränkler. Here you have the situation, and of course for this particular data set it has been done by Szymon Borak. This is the Hennen-Quinn model. This is the corresponding Z model for the AIC. Now, for the electricity data, we used, I shouldn't say we, it is a paper of Szymon Borak and Rafael Veron of a moving window from 1999 to 2000. It's moved for 2 years until 2002. And one looked, I mean, the alternative approach there is sort of a functional principal component approach where one looks at principal components applied to these piecewise constant curves. And if you look at the errors here, so this would be the corresponding series, but if you look at the errors, the in-sample fit in this case, I don't know, is Szymon there? Have you done an out-of-sample fit with this yet? Huh? Yeah, it's not here, but it has been done, but I'm showing only here the in-sample errors in comparison to the principal components. You see this model fits the data much better than the model that has been done in this electricity demand literature before. You can also see it when you look at the in-sample error of the DSFM model, which are these blue curves for different basis functions. Yeah? Of course, for basis function 6, you fit more. That's why this is from top to bottom. So this is the corresponding fit for 6 basis functions. But again, it is open in this context. So last, I would like to show you this so-called fMRI analysis. We hadn't planned this, but when we sent this paper to JASA, they said, this looks so interesting, it must have applications in biostatistics and in medicine. And so I went to a colleague in the Bernstein Center at the Charité. He said, why don't you try to analyze this data set where we take a scan every 2 seconds. Altogether we have 290 scans, and they see a bench, a phone, or a motorbike rotating in different colors. And our analysis has shown 4 data points, and we used 405 B-splines. Okay, this is the basis function M0. This is the next one. We are in discussion with these guys. So we have an interpretation for that. So these are different slices of the brain, but they don't like this sort of global analysis. They would like to have a local model. So we'll work on maybe local neighborhoods and then apply this DSFM approach further. This is the second basis function, and finally the 4th basis functions. And out of this fMRI data, you get, for example, these Z curves. And I'm not sure whether we have, and then you get different stimuli responses depending on whether you see a bench or in a different color. At all these times you have a certain stimulus, and you see here the median on the stimuli, and this is ongoing work. The idea is later when we refine this model and understand our fits better and have more interpretation, the idea is then to use this structure to discriminate against objects seen. Yeah? So the idea is to use fMRI to detect then or classify later whether a person has seen a bench or a motorbike in certain colors. So let me come to the end of this talk. So what I have shown you is a class of models. What I've shown you is a very general class of model, namely the so-called dynamic semi-parametric factor model. We have shown you that the estimating the Z's has no cost in terms of tracing out the covariance matrix of the Z's. So any parametric model that needs covariance estimators is falling into this class of adaptation here. We have confirmed this to you by simulations, and you will see more examples this afternoon or tomorrow afternoon. There are some open questions which I can shortly show you here. I would like to stress one more time, these are the references here. I would like to, these are the theorems. It's of course all on the net. I would just like to show you one more time in one plot what we don't have, or what, maybe this is the graphical thing. So if you have no links in time, panel data boils down to that. If you have functional data, it boils down when you do smooth directed the factor functions. Varying coefficients, if you observe these, it's varying coefficients. If you don't observe these, it's the other way around. And of course, if you observe Z, then you move to a variance equation, but we consider this as a general modeling approach. Of course, the more general the model is, the less you can prove. But we have shown, at least in this set of examples, that the underlying covariance-based structure can be approximated with lower order than the time goes to infinity. Thank you very much. Is this a personal question? Whether I worry about overfitting? Yes, I worry about overfitting, yes. But I need to see first an overfit before I reduce the fit to something more simpler, more regular. I understand your comment in the following way, that, for example, these M functions you would probably start with a function constant, then maybe you have some orthogonal function, and you have some other orthogonal function, maybe then some parabolic function. Yeah, you can do that. But at the end of the day, you will ask yourself, is there maybe more structure? And then you have to increase then your set of orthogonal functions. What we want to do is use a completely, say, descriptive, very flexible approach that means possibly overfitted, that we then reduce. And you can interpret in this paper in financial econometrics, as the kernel smoother, we got less variable functions. So we could really interpret it like in the yield curve analysis as level shifts, slope shifts, and skewness changes. My approach is, philosophically speaking, let the data speak for themselves as much as they can, and then let us reduce. Well, I'm happy to, from after this analysis, to do orthogonal basis